PhD student in Paris-Saclay, France, and I was invited to present a recent work that I've published with my director, Mark Barthelemy, about the growth of cities. So first of all, I'd like to thank all the organizer for this invitation. And I had the opportunity to take a look at a couple of videos from the previous talks at this seminar. And I have to say that I found them very interesting. So I will probably come back to the next seminars if you allow me to. Second is that I like to give you a bit of background. So I consider myself as a statistical physicist. So as you can see, I'm working for the Institute of Theoretical Physics, which depends from an atomic energy research department. And this does not look like something which is similar to cities. So let's just say that statistical physics is actually the physics which studies the big systems with many particles, many interactions, stochasticity, nonlinearities. And if you consider like people as particles that are stochastic, nonlinear with many interactions, you see that it is actually quite easy to drift from pure theoretical physics to more social systems. And in the social system, I would say that cities are the least social systems of social systems. So once you've seen that most cities in the world actually exhibit the same patterns of networks or economies or population distribution, it is actually natural to make this move from pure theoretical physics to social sciences. So this is why I will first start by explaining why we model cities and how we do it. And then we will more focus on a specific part of the city modeling, which is the modeling of urban population and the distribution of urban population in cities and across cities. So as I just said, the reason why we aim at modeling cities is that in the first order, cities, regardless of their size or their place in the world, form similar systems, and these similar systems justify the use of a universal framework of modeling. So this is what we expect from a science, actually. We see in nature or in social system things that look similar, and we try to put them together as much as possible by proposing a universal framework of modeling. So this is why we aim at building what we call a science of cities. And this science of cities try to understand and to explain quantitative phenomena in cities. So the science of cities is that is shared between geography or economics. Well, I think what is important from the point of view of a statistical physicist is to understand quantitative phenomena and not just make qualitative observations of cities. So once we have said that, in this framework of modeling, I would say that the fundamental questions of city modeling are what we expect from a city, people who live in the city, economic activity, people who work in the city, and a network. And the network is very important because the network is what connects people who live in the cities and people who work in the cities. And you see that in history, actually, cities have started to expand very sharply at the moment that it was easier to travel on longer distances. So it's actually very important to understand the problem of transport networks when you consider cities. So these three things are like the most fundamental questions in the science of cities. And today I will mostly mostly focus on the first point, the understanding of urban population distribution. So before we start, a good question that you might raise is what a city? What's a city? It's actually difficult to define what a city is. You can rely on the administrative boundaries or on more complicated definitions. Usually we refer to geographical definitions of city that delimit cities are a set of people who work at the same place or commute to the same center. So that's which this is more or less what we will define as a city. If you have any question during the presentation, don't hesitate to interrupt me. I think it would be easier if we answer all the questions during the talk and not, and then we'll have a second round at the end. So, in the understanding of urban population distribution, A classical paradigm is a Zipf law. So you've probably already heard about what we call Zipf's law for cities or for words in a book or etc. So Zipf's law is a static law which for cities states that if you take a system of cities like a country or a territory, and if you rank the cities by populations in a log-log scale, you will have a line, and so it means that if A is the biggest city in your countries, you will have twice you will have two cities with population half the population of city A, four cities with population a quarter of population of city A, etc., etc. So if you take a city, you always have twice more cities with half the population of the first city. So this is a very typical static law that was observed for the first time at the beginning on the 20th century. Here you have an illustration of what it gives for the 135 largest US metropolitan areas in 1999. So here the biggest city is here. I think it's New York City. And if you plot the rank of the log of the rank versus the log of the population, you see that you have something that looks like a line. So it's an important law because actually it says that there is no typical size for a city. So we should not think as cities are something that are more or less always the same times, which would be some sort of optimal size. But actually the distribution is quite heavy and heavy-tailed. So there is no typical size for a city.
Can I ask a question,
Yeah,
Vincent?
sure.
So obviously you said that it's difficult to define what a city is, right? But
Yes.
intuitively we know or we feel that there are cities which are large and towns or whatever you want to call it, which are small on the other side. And I see here that they're only taking 135 of the largest cities, which is not a huge number, right? There's
Yeah.
thousands and thousands of population centers. So does it hold if you go much further down the other side?
Uh,
If you go to towns that only have 1,000 or 2,000 people?
The answer is no, and you have already understood half of the presentation, so that's fine for you. No, the answer is no, and this is something
Okay.
really important that I will show in a few slides.
Okay, thank you.
So this is a static law, and at the same time, actually in 1931, Gibra defined a dynamic law for cities. So let Si be the size of the city I. We can write the population dynamics of the city as some sort of stochastic differential equation with noise. And so Gibra considered a Gaussian white noise and said that the partial derivative over time of the population is some sort of a multiplicative process with a random Gaussian noise. So if you look at that, you'll see that this result yields a log normal distribution for the size of cities, which is different from Zipf's law. So actually, in this framework, there is no steady state, and Zipf's law has no reason to be the solution for the distribution of cities at large times. So we have a contradiction between these two results, and these two results were conciliated by Xavier Gabet, in 1999 in a very famous paper for urban economics. So what Gabet did was just taking Gibra's law and had a reflective barrier that prevents cities from becoming smaller than a certain threshold. So if you change the stochastic differential equation and add some sort of nonlinearity at a certain threshold S mine, under certain assumptions, this equation leads to a steady state distribution, which is Zipf's law, and with a certain Pareto exponent. So I will often refer as Zipf's law or Pareto law. For me, it's the same thing. So just a way of rephrasing it. And so if you take S mine to be 0, then you observe Zipf's law with Pareto 1, which is the true Zipf's law. So uh, this is how Gabet reconciliated the static law and the dynamic law. The problem of this model is that first, it is actually an untested ad hoc assumption. So You just say that there is a reflective barrier when cities that prevents cities from becoming too small, but that does not really make sense in nature, and or at least it was not tested. Uh, you also remain in this sort of paradigm that cities that you need a steady state for cities, whereas actually cities are out of equilibrium systems, and most of all, actually, it doesn't match the data. So this is what we will see. Uh, in the recent years, there have been many meta-analysis on Zipf's law and Zipf's exponent. And what people did was like testing many countries with many cities and different numbers of cities in the tail. And depending on the country, depending on the number of cities in the tail, depending on the fitting method, actually the discrepancies for Zipf's exponent is very large. So you see here that this is a geographical paper from Clémentine Cotineau. The distributions of Zipf's exponent values can range from 0 to 4 with a mean which is close to 1, but it's just a mean, and the distribution is very large. So this is not really this does not make Gabé's model very relevant, and we need at least to understand why these discrepancies are so large and so common. So this slide is actually about what Rodrigo said earlier. Actually, a very important thing is that the Pareto exponent tau that you will measure for Zipf's law depends on the number of cities that you include in the tail. So before we've seen that for 131 cities in the United States, the Zipf's exponent was close to 1. So we were somewhere like there, somewhere about here. But you see that if you take more cities or less cities, or if you take a different countries with more cities, actually there is no reason to believe that Zipf's law is a good way to describe the distribution of populations across cities. So this is actually kind of just an artifact, which means that if you take a specific number of cities and if you try to measure a Pareto exponent, you will find a Pareto exponent, but this is actually not the right way to do it. You should, before having a model, you should, well, I will explain a bit later, but let's just say that we have too much focused in the last years on measuring Zipf's exponent, whereas there was no reason to believe in Zipf's law. So at this stage, I think, this I will explain later. At this stage, I think we need to start over and try to build a new model from a bottom-up approach that will start from very basic assumptions on cities, and then try to understand how cities evolve over time, and if we can find a static distribution for cities. But let's start with very basic assumptions about how cities grow. So very basically, it is very natural to say that urban growth is the result of two effects: natural growth, which means the number of people who die minus the number of children were born in the year, and migrations. So these two effects are what makes a city, what make the city population grow or decline. So if you consider a system SI of cities, then you can very basically just a balance equation that the increase of population over time is the sum of these two terms, the migrations and the natural growth. But
sorry,
what,
can I ask,
yes?
Can I ask a question? Do you know the migration, is that just including urban migration, i.e. London to Birmingham, or does it include rural to urban migration as well?
That's a good question. So actually, it depends on your data set. So,
Okay.
So far, I will distinguish between interurban migrations between London and Birmingham, and migrations between the countryside and the cities. So actually, we do not have much data for rural-urban interactions. We have only data for interurban migrations. So this is why I will make here a small, I will use here a small trick. I will actually put together what I call the natural growth with migrations that are out of my system of cities. So all these migrations between cities and rural towns that I do not consider because I do not have the data, I will put in what I call out of system growth, and
Right.
the interurban migrations that I have in my data set will constitute what I call my migrations within the systems. So this is
Thank you.
just a small trick that I use because I do not have enough data to include all migrations between towns and cities. And now that I have these two terms, I will just try to understand how they look. So we'll take a look at the shape of the out of system growth, and then we'll take a look at the shape of the migrations within the systems with empirical data. So maybe yes. So in the following, I will use 4 sources of data. French residential migrations between 2003 and 2008, US metro area to metro area by migration flows between 2013 and 2017, British interurban migrations between 2012 and 2016, and Canadian internal migrations between 2012 and 2016. So in these 4 data sets, if I fit what I call the out of system growth rate, which is the sum of the natural growth and the migrations that are not in my system, so migrations between cities and small towns, but also international migrations. So people who move from Paris to London will be actually in that part. I see that this out of system growth is following a very basic normal law. So it's a very simple system. The mean is close to 0. So you have basically almost the same chances to have an increase or a decrease in population from that part of the equation. And there's actually not much to say about that. That's just a normal law as it was in GWA. So once I've said that, I can just rewrite the first term as a multiplicative Gaussian white noise as it was in GWA. Now for my second term, the interurban migration flows, I can write it as a sum over for each city I, the neighbors j of the city I, and I just said that the migration between cities I and j is the number of people who have moved from j to I minus the number of people who have moved from I to j. So this equation is fine. This equation is pretty low level actually. It is similar to a Bouchot-Mézard model in statistical physics. You see that if there is an exact balance of migration flows, the equations becomes equivalent to Gibrat's model. The only problem is that this equation is very general and actually difficult to use and to solve. So we need to change it a little bit, and we need to explicit the set of what I call the neighbors of I, so the cities with which cities I exchange inhabitants, and we need to explicit also these migration flows. So how can we simplify this balance of migration? So this is what I said. We need to find the number of neighbors of city I and the flux between 2 cities. The number of migrations we can fit in all the data sets we have with a very simple law. So the number of cities that can be considered as neighbors of city Y is the population SY of the city Y power to the gamma, with a gamma which is around 0.5 in most countries. So it is just a sublinear scaling form from the number of neighbors. About the flux, it is very usual in spatial economics to resort to what is called the gravitational model, which says that the flux of migrations between 2 cities I and j is proportional to the product of the city sizes power to something divided by the distance between the cities power to something. So this is very basic assumptions that we've also fitted for our data sets. And what we've seen is that actually distance effects are not really relevant and can be discarded as being second-order effect. Actually, what we say is that if you just use a very basic gravitational model, you explain a good part of the noise, but most of the noise is not explained. So you need to take, you cannot neglect the noise. Fluctuations are very important. And so you have a sort of trade-off between explaining as much of noise as possible, but with by the cost of adding parameters, or trying to keep as few parameters as possible at the cost of explaining less noise. And so what we did is that we wanted to have an equation that is self-consistent in populations. And so we discarded distance effects because like distance is not so relevant. And so we'll just put distance effects in the noise, and then we will try to understand how the noise works and to find what the shape of the noise is. So once we have discarded these distant effects, the flux between the two cities can be rewritten as a product of the populations of cities power to something times a certain x, y, j, where the random variables x, y, and j's have an average equal to 1 and encode all the noise, including distances. And what is important is that we cannot neglect the fluctuations of this random variable like x, y, j. We cannot neglect them. They are too big. So it is important to keep that noise. We cannot approximate the flux by the average of the flux.
Can I ask another question?
Yes, sure.
So it's about that random variable. So do you have any other assumptions besides the mean, the average?
Not yet, but we will have in a few minutes.
Okay.
So at the moment, we just know that the mean is by definition equal to 1.
Okay.
But we have just defined xyj as like the flux divided by the population power to something. This is just all we have said. We have no idea about the variance, about the fluctuations, or about the shape of the function.
Perfect. Sorry, I keep jumping ahead. I'm gonna wait.
That's fine. Now, if we define what we would call like the flux per inhabitant, so it would be ijy. So this is like the number of people that would leave a city divided by the population of the city. We see empirically that on average, we have some sort of detailed balance, which means that the probability for a person to move from city I to city J is almost the same as the probability for a person to move from city J to city I. So actually the ratio of the migration probabilities is just proportional to the ratio of sizes. So this is important because it says that on average, you have as many chances to move from a certain city I to a certain city J than the opposite movement. So this is not so intuitive, and it is also just an average, but it means that there is no global trend for people to move from small cities to big cities, or from people to move to big cities from small cities. On average, there is no such effect. Averages are equal. But once again, fluctuations are very important. So what do we have at this stage? We have always our equations. We have understood that the flux were like proportional to the product of the sizes power to something times a certain random variable, and that crucially fluctuations are non-zero. So let's just redefine some sort of renormalized random variable big x y ij. Then so if we do that, we will just have this sum as being a sum of big x ij, and we observe that these new random variables are evitail. So this is the crucial point. The crucial point is that if you look empirically at this density of these variables, you see that the tail is very heavy and it decreases very slowly, and it decreases more slowly than a Pareto law with exponent 2. So this is what I call evitail distribution. It's when the asymptotically well, you understood. The distribution is equivalent to a power law with exponent alpha, which is less than 2. So it is very important to understand that these random variables are distributed according to a broad law. And once we have said that, so we have our new equations that I have just rewritten as to make appear a sum over these broad-tailed variables and heavy-tailed variables of tail exponent alpha. And then I will use a mathematical result, which is the generalized central limit theorem. So you all know that if you have a sum of random variables with mean and average, then the sum is equivalent to a normal Gaussian law. But when you have no mean or when you have no variance, you can generalize these results. And instead of converging towards a normal Gaussian law, the sum of your random variables will converge towards a Levy law, so what is called a Levy law. Levy's stable laws are a family of laws that are complicated to write explicitly. You can write them in the Fourier space, but these laws are asymptotically equivalent to power laws with an EVTL and parameter alpha less than 2. So what the generalized central limit theorem states is that this sum of variables over a certain number of neighbors that we have said to be proportional to the size of the city, not proportional, but depending on the size of the city, this sum of random variables behaves like a Levy stable law of parameter alpha, alpha being the same alpha as the tail exponent of the variables x, I, j. So, so this is our main empirical result, is that actually when we look at that in the real life and on the data sets, if you look at the cumulative functions of this sum of big xyj, so this sum of xyj in the real life is just the sum of migrations in a city. So like it's the results of the migrations to the city I. So it may be positive if more people are moving in the cities that are leaving the cities, or negatives if there are more people who are leaving the cities than people who are moving in. But this is just a renormalized form of the resulting flux or migrations in the city I. And you see that actually it's more relevant to fit the data in real life by a Levy stable law than by a normal law, as it was the case in Gibra's model. So is it a big deal? That would be a question. Let's just say that. So we'll just finish the work by writing our final equations. So we say that the number of neighbors of city I was proportional to SI power gamma. So we can write a final form of equation, which is a stochastic differential equations with two noises. A first normal Gaussian white noise, which is the combination of the natural growth rate and international migrations or migration between cities and towns, and another term which accounts for interurban migrations, and which is a multiplicative noise product of a Levy noise, which is different from a Gaussian normal noise. So you actually so Gaussian normal law is just a Levy law with parameter alpha equals to 2. So the Gaussian noises are a specific case of Levy noises. So this is a form of generalization. And if you understand that, so what's a Levy noise? It's a heavy tail noise. So when you think of noises, you will intuitively consider that if you have a sum of random variables, and if you add a n+1 random variable, then you are more likely to think that this new variable will not change the sum. So the sum of the past is more important than the last term. But this is a typical reasoning for a normal law. In the Levy case, it's not in the Levy framework. It's not always the case. So when you have a Levy stable law, the last element you add to the sum may be as big as all the previous events. So this is what is really important. Is like what I don't know if you've already heard of Levy flights. So if you have a Brownian motions, it moves like at a certain positions, and sometimes you have a very big drift towards another position, and this is called a Levy a Levy flight, and this is what a Levy noise is about. It's about big shifts at some point. So once we have said that, you can understand that actually Levy noises are more important than normal noises. So you can actually approximate the normal Gaussian noise by its mean, and just rewrite the equation as a one noise equation with a noise which is a Levy noise. So this is an equation that is self-consistent in the population. The population is the only parameter that we have. We just have to measure two exponents, an exponent beta for the size and an exponent alpha for the Levy law. But actually, for simplicity, we may assume that beta is close to 1. It doesn't really change the idea behind the equation. So we actually just have a one parameter self-consistent equation for the growth of cities. So can we solve this? The answer is yes. I will probably not delve too much into the results, but there is a solution in the form. So like every stochastic differential equation, there is a corresponding Fokker-Planck equation for the equation. In this case, we used what is called Ito's convention in contrast with Stratanovich conventions. And so this equation can be solved, and it leads to a power series, which is quite complicated. So we do not, I will not explicit all the terms. I will just make a few comments about the first order and the second order terms. So when you look at these solution, you see that the probability distribution of city sizes is dominated at large size by the order k equals 1. So the first order, k equals 1, is the biggest one at large sizes, because these terms decreases to 0. And it converges towards the Pareto distribution with exponent alpha, which is different to 1. So at large size, you see that we find something that is akin to a Pareto law, like Zipf's law, with just an exponent alpha, which is different to 1. But crucially, the speed of convergence towards this power law can be estimated by the ratio of the two terms k equals 1 and k equals 2. And you see that if the second terms does not decrease fast enough, then you will not converge towards this Pareto law. And what we've seen is that empirically, at the time and size scales that are considered in real city systems, it is very unlikely that the first order term is dominating. So you cannot in real life drop the second order terms. So it means that you need to consider all the terms at the same time. And there is no way to approximate this solution in real life by a Pareto equation. But you can also see that there is a scaling form from the probability distribution. So you can try to collapse the data. And if you collapse the data, you see, so this is for France between the 19th century and today, you see that a scaling form for the probability distribution has a ratio between a certain function of the ratio of the city size divided by the average city size. This function divided by the city size gives a universal data collapse for France. So actually, even if you cannot explicit the solution for all terms, you see that data actually matches the solution in the form of this scaling relation and this data collapse. Another thing that you can think about is that the upper tail of the city size distributions may be mistaken for a Pareto law. So if you naively try to fit these solutions by a Pareto law, you are very likely to think that you found a Pareto law. So this is crucial. It means that, for example, here for France, the real alpha value is about 1.3. So if we were at size infinite, we should have a solution that is close to a Pareto law of exponent alpha 1.3. But if you fit the solution considering before that you want to find a Pareto law, you are very likely to find a spurious apparent exponent alpha that will look like a Pareto exponent, but which is not a Pareto exponent. So the upper tail of the city size distributions may be mistaken for a Pareto tail. So this is why so far it has been very common for people to observe Pareto laws in city tail distribution. It's just that actually it's very easy to fit a Pareto law. So but what is important is that depending on the threshold and on the number of the cities that you put in the tail, just as we've seen at the beginning of the presentation, the value of the exponent may change a lot. So it is not relevant to do like that, but if you do like that, you will find the Pareto law you want to observe. What does it change? Actually, the more important changes that we observe with this new equation is more about the dynamics than about the static solutions. So I will now speak about what I call the splendor and decline of cities, and we will try to understand how this equation changes the way cities have evolved over time and in history. So actually, when you compare what so if I use a certain way of plotting city populations over time, which is called rank log, and it was proposed by Batty in 2006. So I can for every year I can rank cities by their populations, and I can plot the rank of the cities around the clock. So here, for example, for France, I show you that here at the border of the circle, you have the biggest cities, then you have the second biggest cities, and you have here the smaller cities. And you see, every line has a color, and every color is a city. And the rank of a city evolves through time. So for example, Paris is the biggest city in France since has been the biggest cities for the last 150 years. So you see that the red line here is always the same, and Paris is always the biggest cities. But for smaller cities, you have actually very intermittent and chaotic moves. So you see that there are cities that have dropped from a very high position towards a very low positions, or on the contrary, cities that were very small and that have become very large on a short time scale. So there is another clock just after that will be more explicit, but let's just observe from far away that what is real life is very intermittent and is more likely to correspond to a Levy model than a classic Gibra-Gabay model. Actually, in a Gibra-Gabay model, the rank of a city is very likely to be always the same with very small variations. So if you plot the rank of a cities in Gabay's framework, actually you observe circle, which means that cities have no reason to grow or to decline. They're just in the ranks of cities, they stay at the same position. But nature is different, and cities in real life are different, and Levy fluctuations are much more able to reproduce this turbulent behavior and these turbulent properties of the dynamics of cities through time. So I've given you here a few examples. So as I told you before, Paris is the largest city, has been the largest cities in France for the last 150 years. So it's just a very simple line. It's actually compatible with Gabay's framework. Another city, which is Saint-Malo, has also a very natural and not turbulent behavior. But you see that some cities like Aigues-Mortes in the south of France have on very short time scales, like in 10 years, drifted from a very low position towards an important position in the ranks of cities. Or on the contrary, another city like Decazeville, which was a coal mining town, has decreased from a very important position close to Saint-Malo to a very small position in the rank clock in a few decades. And so this is really important because this was Gabbe's model was unable to reproduce these sorts of behaviors when a city can actually decline on very short time scale, or on the contrary, become very great in a few years. So the best example is actually San Francisco. In 1850, there were like 1,000 people who lived in San Francisco, and 10 years later, there were 100 times more. So this is what we need to understand, is that like it's very natural to think that cities can grow very fastly. You just need to find new resources, or think that urban planning policies has attracted people to a city. When you do that, you are very likely to observe big migrations on short time scales. And we needed a sort of equation that was able to reproduce that. And Levy fluctuations are able to reproduce that, in the contrary to more classical Gaussian white noise fluctuations. Another way to see that is that if you look at the maximal rank variations that will happen for a city over time, over a certain number of years, you see that Gabbe model is not able to to reproduce very, very large rank variations. So in a very classical Gibra Gaussian white noise framework, it's very unlikely that you observe a city moving from a low position to a top position, whereas a Levy model with huge variance is much way more apt to reproduce such behaviors. So just I will now jump to the conclusion that let's just sum up what we did. So we built a stochastic equation of growth for cities on the basis of micro-level considerations that is empirically sound for at least 4 datasets at different periods of time. We've seen that it is the existence of non-universal and broadly distributed fluctuations of migration flows that govern the statistics of city populations. And this model is able to statistically reproduce the turbulent microdynamics of cities that rise and fall, in contrast with previous Gaussian-based models of growth. But what is important and what it changes is that it is not the big events that make up urban demography and decide the fate of cities. So in particular, the demography history of cities is not just a sum of small noises that add up over time and give a city. No, it is the waves of urban migrations, one-off but major waves, that explain the most why some cities may emerge or disappear on very short time scales. And so in that framework, the success of cities is more explained by external shocks that can possibly be induced and controlled than by the accumulation of strictly random and factal effects. So I like to think about this result as something which is very optimistic, because it just says that urban policy and planning decisions have a major role to play in strengthening the attractiveness of a city and in making a city great and attractive. Whereas like previous frameworks of modeling were more fatalistic, in the sense of that they say that there was no reason for big events to change the fate of the cities, and cities were just the result of multiple and random small shocks that were not related to some sort of specific events. So actually specific events control the cities. If you find new resources, if you have a very attractive policy, you can make people come to your city. And on the contrary, cities like Detroit in the United States may have big populations drops on very short time scales if at some point your industry collapses or decline. So I just like to finish by a French quote from a quote from a French writer who was not very famous, Paul Nizan. He was a philosopher from the beginning of the 20th century. He was actually the student roommate of Jean-Paul Sartre. And he said in one of his books, Aden Arabi, ces mouvements du désordre n'imitent pas longtemps les allures de la liberté, which I could translate by these movements of disorder do not imitate the shapes of liberty for long. And I think this is actually what we've done. Just before we thought that disorder was something that was uncontrollable and some sort of intrinsic process that you do not control. Here we've seen that for cities, shocks are actually a kind of expression of liberty. So it is a way to reconcile like social sciences with this very quantitative and mathematical approach, is that we do maths, but we do not do maths and physics to take the freedom out of the social sciences. We just illustrate by that quantitative phenomena actually obey very stochastic and very stochastic effects. And we've seen that stochasticity can actually represent the very different behaviors that individuals can have in their life and in their decisions. So here are the references for the different figures and papers I have cited in this presentation. And I will be very glad to answer your questions if you have. Thank you for your attention.
Thank you. Vincent, that was very, very interesting and a cool, positive message at the end about mathematical modeling. So are there any questions for Vincent? You can also ask something in the chat if you want, and then we can ask. Or...
I guess a question, if you go back to your slide on 2 slides back, I think.
Here?
Yeah, this one, yeah. I guess the question is, related to this is, for cities, obviously that had their heyday in an industrial era, like the one you mentioned. I don't remember the name of the one that you mentioned before, but there's plenty in the UK that have had the same fate in a sense, right? And I agree with you. Like it's a very fatalistic outlook in the city. They just don't see, or people who have ambition within the city just don't see the city going anywhere. And I'm thinking, are you thinking about questions about how to relate this back to urban policy and planning, and how a city can kind of kickstart its regeneration in some way?
Yes, indeed, yes. No, it's really important, yes, to think of it as like a link with what policies can do, and I think it also says that like cities have their own history, and so here we have a general framework, but then each city is different, and each city must study its own past and work on its own policies and decisions of urban planning.
Yeah, thank you, and thank you for a really good talk.
Thank you very much.
I also have another question, if I can. It's a bit about, because, well, so we are here the network seminar, so often we think like in terms of networks. And you have made use here of like a gravity model, right? And sort of how different cities interact, which is somehow not really a network, right? Well, I mean, obviously it sort of works for your data fitting, but I'm just wondering, do you think that's just something that wouldn't help much in the modeling, or just, is it, you know, a convenient assumption at this point, or how do you see?
Well, so actually, yes. So we think the system of cities as a network. So we have cities that are edges, that are vertices on a graph, and fluxes are the edges. And so a good question, actually, for it's more of an economic question, is to understand how this flux between 2 cities can be explained. And this is not something that we do not do. We just say that it is actually obvious and very easy to observe that this flux is proportional to the sizes of the cities, but we do not try to understand it more. And actually, there is work to do to explain why there is a certain flux between 2 cities, between a cities I and a city J, And this question is more of an economic question, because like this is where you have to look at all the possible variables, so the distances, but maybe the difference between the salaries or the differences between the ages. And so this is more of, this is a complicated question that we did not focus on.
Yeah.
But of course there is work to do in that part of the study.
And if I may ask a follow-up on that, so is the most important part of the gravity model the fact that it depends on the populations, as INSJ?
Yeah. Yes.
So that's an assumption that you need in order for all of the simplification of the equation that you do afterwards, right?
Yes, indeed.
Okay.
Yes.
So you wouldn't be able to put something like another model, like the radiation model, in there.
Well, actually, we tried the radiation model, but it was not really convenient in this framework. And actually, mathematically, and also in the radiation model, you need more complicated. You need more information in your data set, because you need all the distances between all the cities. So it's a bit more complicated to implement. So we remained at the stage of the gravitational model.
Nice.
Yeah.
Any other questions?
Yeah, I have one more, if no one else.
Yeah, sure.
Just you mentioned at some point that like a very similar model was used in, was it wealth condensation or something?
Yes, wealth condensation.
Yeah,
Yes.
was it, so that's a model where they also had these fluxes, or?
So if I remember, so the wealth condensation model is a model of money flux in an economy. So you just have individuals who have a certain amount of money and wealth, and depending on the rate of interactions between individuals, you see that if you have a stochastic model, at the end, the money will be condensated in will be very unequally distributed, and so some individuals will have most of the money, and others will have just a little of the money.
Yeah.
And so the Pareto exponent of this wealth condensation depends on the rate of exchanges within the economy, I think. So
Okay.
this is what it looks. This is what. So the equation is actually this one. So you have let's say SY would be SI would be the money of individual I, and so the variation of money is a stochastic noise plus exchanges with the other individuals.
Okay. And is anything know there about like these fluxes? Is there also something like Levi, like heavy-tailed?
No, in the model they did not consider Levy noises.
Okay.
So
but you can still get these Pareto without Levy, right?
Yeah, yes, they have a Pareto solution. But what they do is actually they try to solve the model theoretically. So they make assumptions on the fluxes. So they just say that the fluxes are constant, or I don't remember well, but I think that just say that J is average J, and they simplify that terms, but without considering Levy fluctuations.
Yeah. Okay. Okay, it's interesting. Any other questions? Otherwise, I think we can thank Vincent again for the great talk. Really interesting.
Thank you very much. Super
Yeah,
nice.
thanks a lot.